So we're very pleased to have Sandro here today, and Richard's going to introduce him.
Hi. Well, like Catherine said, we're very pleased to welcome Sandro Tacchella to Heidelberg, twin city of Cambridge. So Sandro is based in Cambridge, assistant professor at the Camberley Institute and also the Cavendish Laboratory. Sandro, as you most of you will know, as one of the most active researchers in galaxy evolution. And I think the particular thing which is impressive to me is the fact that you managed to do this on, I think, 3 fronts. You actually are involved in some theoretical numerical simulations, and you were actually played a role in the calibration and the data analysis or pipeline of the NIRCam. I think you'll be showing some data there later. And of course, you are one of the leading members of the JADES project to do spectroscopic and imaging studies of the distant universe with NIRCam. So I think we're going to hear really from the cutting edge this afternoon. Sandro started his career as a PhD student at the ETH Zurich. He moved on to be a CFA fellow at Harvard. And then after that, he was, I think, for a year or so, an assistant professor at the physics department of UNIST in Uzlan. That's Korea, right? Korea. Before he went to Cambridge in 2022. So without any further ado, Sandro, welcome, and please take it away.
Thank you very much, Richard. Yeah, thank you very much, for hosting me and, giving me a great time here. I'm very excited to talk to you today about, galaxy evolution from a very early perspective. So the work that I will be presenting has been done with my research team in Cambridge. Consists of master students and about 9 PhD students. I try to show the works of them and also several postdoctoral fellows. So the group that I'm building up since the last 3 years focuses basically on 3 different elements. So one of them, basically the main one, is really driven by kind of observational discoveries, so the analysis of novel observational data. In the last few years, of course, the James Webb Space Telescope, but also with upcoming instruments such as the Moon spectrograph that I will be touching on at the very end of my presentation. Then in order to analyze these data, we have been developing new analysis tools, and I try to mention some of these as well. This has to do with understanding, for example, how we can estimate stellar populations in the early universe or the kinematics of galaxies. And then last but not least, also theoretical models. Here, we are particularly interested to understand how we can compare the theoretical side of galaxy formation with the observational side. So thinking about radiative transfer models, but also much simpler empirical models. So as I said, I want to take you basically back in time to kind of early galaxies. The way that we are thinking about this is with these very kind of fundamental questions that I think are still wide open. Understanding in particular, how did the very first black holes and stars and galaxies form in the early universe? What kind of sources reionized the universe when we went from basically a neutral intergalactic medium to an ionized intergalactic medium? How do galaxies chemically enrich? How does the structure in galaxies form, in particular bulges and disk components? But also how do galaxies in very broad scheme, regulate their star formation and also quench at later epochs? So the framework that we are trying to address these questions in is our standard cosmological model, lambda CDM. Again, the lambda stands for basically the dark energy component, and CDM stands for cold dark matter. And so this model is very successful in reproducing the cosmic microwave background, so the afterglow basically of the early universe, about 400,000 years after Big Bang. And one can put this into simple n-body simulations where we just have gravity and see basically how then the nonlinear structure forms through cosmic time. And we can produce maps such as those that show basically the cosmic web on large scales. Here we're talking of tens to hundreds of megaparsecs. So we can then compare these distributions of dark matter halos with the ones from galaxies and find that we can really reproduce the large scale structures, so the clustering and the overall distribution of galaxies very well. This shows you some early work basically of how the galaxies cluster from redshift surveys to the millennium simulations in this example here. So when we think about the paradigm for galaxy formation evolution, it's basically quite simple, in particular early on, where we have these dark matter halos. In a lambda CDM, they're growing bottom up. So we have smaller structures forming first, and they are then merging to form larger structures with time. And the baryons, the gas, basically sees these potential wells, is able to basically fall into them and then cool and then really sink to the very centers of these dark matter halos and then start formation of stars. So when you think about the early star formation, there are many different regimes, and of course, you can just talk about this in great detail, and it's very interesting. When you think about dark matter halo masses of the order of, 10 to the 6, 10 to the 7, that's where we think the very first stars, so-called POP3 stars, are forming. These are very difficult to detect with current facilities, including the James Webb Space Telescope, and the hope is that future 21 centimeters experiment or gravitational wave experiments will able to tell us more about this phase. Then the real start for galaxy formation is when we have atomic cooling halos, where we have the idea of the first stars and galaxies and really taking off. And then, towards more massive halos, we have then galaxies and supermassive black hole formation with much more intense star formation. And so we think that, POP3 star formation plays a crucial role in actually setting the initial stage for then the formation of the very first stars and galaxies with, with more chemically enriched systems, basically on the redshift of, 10 or 20. So now the last ingredient that we need, that kind of we figured out 20 or 30 years ago, is that, once we cool and form these stars, we have to regulate this growth. Otherwise, we would overproduce basically galaxy stellar mass function. And this is shown here. This shows you the number density of galaxies of different stellar masses. And what you see here is how, the galaxy mass function. This tells you really how many galaxies do you have in a given mass bin. And we can compare this with red dashed line, which is basically the dark matter halo mass function, so the number density of dark matter halos. And then you rescale this by the baryon fraction. So you assume that basically all the gas that you have available form stars. This would basically be the prediction. And what you can see is there is a large difference both at low mass and at high masses, indicating that you need to somehow suppress galaxy growth or star formation growth in galaxies in the low mass halos and the high mass halos. And so this leads to the idea that, we need feedback, some kind of heating basically from stars and black holes to prevent overcooling. So when we think about this in a more cosmological context, we can now go off and of course measure how many stars are forming in the universe as a function of time. So this is showing you here look back time. So we're looking further and further into the past. And this shows you redshift. Again, we're going to higher and higher redshifts. And again, we talked about recombination. That's where the CMB was emitted, about the redshift of 1,000. Then we had the dark ages, where basically, the dark matter halos, population started to grow more and more, and the gas was able to start condensing down. And then we had cosmic dawn, where we really had the formation of the very first stars around the redshift of 20 or so. And again, I said already that, there was this epoch of ionization where we had then basically that these stars and black holes started to illuminate the universe, and these ionizing photons reionized the universe, going from a rather neutral universe to an ionized universe. Now, for the last 10 years or so, we have been really heavily studying the cosmic noon epoch. This is where the cosmic star formation at density peaks in the universe. And that's where basically most of the stars in the universe formed. So if you ask a typical star today, it says it was formed around here. Now, how can we describe this? So why does the cosmic star formation density increase and then decrease? And for this, we can actually build very, very simple models, right? So I told you already that we have structure formation bottom up. If you assume a very simplistic so-called regulator-like model where we have a galaxy consisting of gas and stars, we are forming somehow after this gas some stars. You have gas accretion onto the system and also outflows. You can, see that in these equations, you can very quickly approximate the star formation by the accretion rate. So basically you say, the more fuel is coming in, the higher, the star formation rate, the more stars you're forming. And so you can build up, maybe one of the most simplest models, which is saying that the star formation rate in a given dark matter halo at a given redshift can be described by some kind of star formation efficiency times the baryon fraction times the dark matter accretion rate. So you say basically dark matter comes in, you also have gas with it coming in, according to the baryon fraction, and then you are converting this with some efficiency into stars. And so you can go and try to calibrate this. And again, now you see the simplicity comes here because we say that this efficiency doesn't depend on redshift, right? We just say it's a function of halo mass. And you can say, well, what do I need in order to produce, for example, the UV luminosity function redshift 4? And this is how this would, for example, look like. So you have the star formation efficiency peaking at a halo mass of around 10 to the 11. And this, of course, is very similar to what you have seen before, that star formation needs to be somehow regulated and suppressed at high halo mass and at low halo mass. So this is basically exactly the same kind of idea here. So you take this very simple model that you calibrated a redshift force. Again, this is very little physics. You just have an effective model basically for the star formation efficiency, and you just let it evolve. So what happens is that you really just basically calculate how much dark matter accretion rate do you have, how many dark matter halos, and you integrate this up to get the cosmic star formation intensity. And you can see that pre-JWST observations were extremely well fit with such a simple model, right? So again, you get a strong decrease in the cosmic star formation intensity, you know, by 3-4 orders of magnitude, going from redshift 4 to redshift 10. And again, the idea now for this, and this is such a simple model that you can actually, you know, basically reconstruct this by yourself. You basically want to look at the star formation efficiency, right? And then, you know, which is, you know, times basically dark matter accretion rate times the number densities of halos. And if you plot the number densities of dark matter halos, you can see that from redshift 10 to redshift 4, that dark matter halo mass function is moving into this regime where you have high star formation efficiency. So in this model, the strong increase is described by just having basically more and more dark matter halos that have higher and higher accretion rates in this very efficiently forming regime. And that's why you have this very strong increase. So again, this shows you that if you have a very simple prescription for star formation, you can actually explain already, you know, one of the key observables in the universe. So are we done? Well, the answer is of course not, right? There is much more to learn about it, because I told you there's this effective model for the star formation efficiency, but what is really the physics that drives that? And so here it gets much more complicated, right? Because when you think about galaxies, they are basically driven by physical processes on large scale, right? We have the environment that might be important for galaxies, but also by very small scale processes. I told you already, feedback of stars, of black holes might be important. And so they all act together, and the physical processes are interacting with each other on a wide range of different spatial scales, but also temporal scales. And this makes it very difficult, both analytically to follow these processes, but even also numerically. So now moving on to observations even more, and trying to make progress in answering some of the key questions I outlined before. Here, of course, in the last 3 years, there was a big shift going from the Hubble Space Telescope that allowed us to basically trace the rest frame optical emission of galaxies out to redshift 3. Now with the James Webb to go to, basically through the epoch of ionization in the rest frame optical, in particular when we look at some of the key instruments such as NIRSpec and NIRCam. And so, again, I could talk about this telescope forever, literally. So if you have any questions, please let me know. I myself, I'm part of the NIRCam science team. That is, again, the main imager that basically works between 0.6 and 5 micron. And the other key instrument that I will be talking about is NIRSpec, which is basically the prime spectrograph on this telescope. But there are other instruments such as MIRI, and you will see some observational data from MIRI as well. Now, as part of the NIRCam science team, we partnered up with the NIRSpec science team, and we built basically a GTO program called JADES, which stands for JWST Advanced Deep Extragalactic Survey, where basically we want to make use of combining the best of both instruments, right? So you want to take images to basically find and discover the interesting objects, and then you want to follow them up with spectroscopy to really characterize their physical processes. And so these are basically, describing some of the programs I will be showing to you. Again, JADES is kind of at the core of very much, but there are kind of follow-up programs as well. And if you're interested to hear more about those, I'm of course very happy to talk about this as well. So again, the data, I myself been working a lot on the NIRCam data reduction, so really going from the raw images to basically reduced images such as those. So these are really beautiful images, and feel free to basically either Google the survey or look at the website, and you can actually zoom in and zoom around the images, and there is additional buttons you can click to basically see then the spectrums popping up. Again, scientifically, this shows you an image of the sky at 1, 2, and 4 micron. I just want to zoom in on one of the regions to highlight basically the diversity of galaxies. Again, on the screen, it looks even more impressive. But what you see is basically, it's kind of messy, because now we have to start thinking of how we do photometry and measure the light of those sources. And you can see, it's kind of difficult to tell apart, what are actually the galaxies in such images, right? Should I call this one galaxy, or are these 3 galaxies? These are probably 2 galaxies, right? But their isotopes are really strongly overlapping. So there's still a lot of questions and things that we are discussing in telecoms basically every week. So let me move on to the very first question now about how, when and how did the very first galaxies and black holes form. Now, again, this is showing you a very rough, or basically up to 2-3 weeks ago, like the summary of how this looked. Okay, so this shows you absolute UV magnitude. This shows you basically UV luminosity scaled by L star at redshift 10. And the blue crosses show you the photometric sample, and all the colored symbols show you spectroscopically confirmed galaxies, basically above redshift 10 from different surveys. Now, we are currently working on one that is actually in preparation that should come out early next week, which is the new redshift record holder. So at the moment, we're really pushing this limit of redshift 14 now. What this means is basically we are now seeing galaxies in the first 300 million years after the Big Bang. Okay, and so this is basically a new redshift record that is coming out in about a week or so. And again, what you should be able to see is that the spectroscopic samples are a bit biased high relative to photometric samples. Obviously, it's clear, right? It's easier to get spectroscopic redshifts for those systems. But we are currently working hard to try to push this further down. So one of the key things, in particular from the photometric samples, was actually seeing that we see many more galaxies than we expected. And so this is usually referred to as being kind of the overabundance of UV bright galaxies in the universe. And the key driver for this is that the bright end of the UV luminosity function seems not to be evolving that much anymore above redshift 10. And so if you compare this basically with the simple toy model I told you before, right, where we have this very strong decrease in the cosmic star formation at density, we can see that the current number counts in the photometric sample is, factors of 2 or even more above that. So now you can, of course, ask the question, well, what happens? So this is, so the first caveat I think I need to say is that, many of these claims have been made based on photometric sample. We are quite successful in confirming them. So I don't think that will change necessarily the picture, but it's something to keep in mind that, many of these claims is based on photometric samples, and we want to keep pushing the spectroscopic follow-up of that. Now, interestingly, over the last 3 years, after these first claims have been made, models have been actually very quickly being updated. Okay. And so if you want to hear about this, we can, of course, talk for hours about the details of these models. But if you think about this simple equation, thinking about how to predict the UV velocity function as a convolution of number densities of dark matter halos, star formation rates in these dark matter halos, and the conversion to UV luminosities from that, you can already see you could change, for example, the number densities of dark matter halos, right? You can say that maybe we were wrong with estimating the number densities of dark matter halos, and this could, of course, lead to a boost in UV bright galaxies at early times. And so there are quite a few ideas out there. You can change the dark matter models. You can introduce early dark energy, which might also fix other tensions we have in cosmology. The challenge there, I think, is always to come back and say, well, why should we prefer such a solution than just the baronic physics? Because the baronic physics, of course, has a lot of freedom as well. And as we kind of, hint at already at the beginning, because you have many different scales involved, maybe we miss some crucial ingredients there as well. And so I prefer usually to talk more about the physical side when it comes to the baryonic side to change this. And so one interesting idea is to increase the star formation efficiency. Again, in this simple toy model, I told you already that the star formation efficiency in this model is just a constant with time. So, a given dark matter halo gives a certain star formation efficiency. But of course, you could argue maybe the metallicity is lower at higher redshift, and so maybe the star formation efficiency should be boosted. And the idea behind the feedback-free starburst model from Avishai Deckel is that you basically have a low metallicity regime where then the early, feedback processes of stars, like stellar winds, and in particular radiation pressure, doesn't couple very well to the gas in the first 3 to 5 million years. And this feedback delay can lead to basically a lot of very efficient star formation for a very short amount of time. You can also introduce more scatter. Again, in this kind of model, we usually don't have scatter or a very limited amount of scatter. And so if you introduce a lot of scatter, for example, through dust attenuation or stochastic star formation, you can bring galaxies that are basically sitting in lower mass halos, and you can scatter them up to brighter and brighter parts in the UV luminosity function. And so this means that you will be able to reproduce more bright galaxies in the early universe. You can, of course, also mess with this conversion here, right? How do we go from star formation rates in a dark matter halo to the UV luminosity? And there you can play around with the initial mass function. So for the same amount of stars, you produce maybe more UV luminosity. You can introduce contributions from HENs, right? So this is all about star formation till now and not really about black hole growth. It could be that HEN contribute to the UV luminosity function more than we have expected till now. Of course, you can also, mess around with the stellar population models. You can introduce binary rotation in stars that can boost some of these as well. And what I will try to convince you in the next few slides is that it might be actually a combination of several of these processes, right? And you can see this in particular when you look at the spectroscopic samples that have been confirmed that they come in a wide range of different properties, thinking about sizes, attenuation, star formation at HEN activity, and so on. So going back to this figure, let's look at these 4 galaxies. These are basically the first spectroscopically confirmed galaxies above redshift 11. So 2 of them have already been photometrically selected from Hubble in the Hubble Ultra Deep Field, and 2 more have been basically put forward by us and then spectroscopically followed up. And when you go and measure the properties of these galaxies, again, this is very rough. Basically, we infer stellar mass of about 10 to the 8, 10 to the 9 solar masses, and star formation rates of about 1 to 2 solar masses per year. So again, the star formation is similar to the Milky Way. However, it is in a much more compact configuration because the sizes are only basically about 100, 200 parsecs, which imply very high star formation rate surface density. Now, 1 to 2 solar masses per year doesn't sound like extremely high, but again, given the stellar mass they have, the specific star formation rate is actually very high, implying very quick doubling timescales, right? You basically have to wait to double the mass in those systems only a few tens of millions of years. But then they are very actively growing. Now, they are not, nothing that unexpected given kind of lambda, CDM-based cosmological models, basically. So again, this is basically very consistent with what we would expect from observations. Talking about those 4 objects now that are basically at the bright end. Again, these are extremely bright objects. You have to understand that, basically they are, brighter than what you would expect anything at redshift, at these early times. Again, you can see they're all kind of red. This is not very surprising, but you can already see that some of them are basically very compact. Others are more extended. Just a warning, this is a foreground galaxy, so you should really just look at this part here. And when we look at this in more detail, we can, for example, look at galaxy sizes versus redshift, and also looking at equivalent widths of, for example, the N4 emission line. And what you can see is that the emission line properties correlate very, very nicely with the morphological indicators such as galaxy size. So basically everything that is, rather weak in N4, is kind of following the typical size mass relation as, we expect from lower redshift. But the very compact systems here, they seem to have a rather high, rather strong N4. And so why is that? There are many different, physical reasons. We can talk about chemical abundances. In GNC11, we think that it's partially driven by the HEN. And I want to make this point a bit more in detail. So let's focus on this system specifically. So again, here, this is showing you basically the image. We have here a zoom in region. Again, the galaxy is basically extremely compact. We're talking here of a few tens of parsecs in size. So basically the central part is basically unresolved. It's really just a point spread function. And this shows you basically the spectroscopic confirmation of GNC11, again at redshift 10.6, with really a nice slew of different emission lines. Now you might say, okay, well, why do we need the imaging data when we have this beautiful spectrum, right? But you can actually start seeing that there are other dropouts. Again, these are just photometrically, photometric candidates basically at these redshifts. But it seems that these galaxies are not alone. They're usually quite highly clustered. And from this, we can, for example, see that there are about 9 galaxies within 5 co-moving megaparsec, which might imply that this is really kind of an overdensity, maybe with with a dark matter halo mass of nearly 10 to 11 solar masses. And looking at some of the the models of like how do these protoclusters assemble, we might really look into kind of early protocluster and galaxy cluster formation here. But the diversity of pathways in these kind of diagrams typically is quite large. So one has to be kind of careful not over-interpreting this. Now, when we look at GNC in more detail, we can see, there is basically a P Cygni feature in the C4 line. We have, a continuum spectral slope that is consistent with HEN, and also the density implied by permitted line indicate that we are basically looking at, in a central region, into a broad line HEN. And you can use, for example, the magnesium line to infer a black hole mass, which, implies that, that GNC11 contains a black hole mass of about 10 to the 6 solar mass. And so this is kind of interesting because now you start thinking about how do these black holes actually grow, right? We know already of quasars at redshift 6 that have 10 to the 8, 10 to the 9 solar masses. And it might be that the, GNC11 is a prototype of such a progenitor, basically, that you could keep growing such a black hole at roughly Eddington rate or slightly below, and you will end up with a, a black hole that can explain some of these quasars at lower redshift. Now, of course, there are still a lot of question mark of, how do these black holes form? I think an interesting indication is that when we look at current constraints of these black hole masses, where the error bars should be, nearly an order of magnitude, I would argue, we see that these black hole masses seem to be overmassive given local relations between the black hole mass and the stellar mass. And so it seems that you have very efficient, compact star formation and possibly also black hole growth in the early universe, whether these black holes just grow very effectively, very efficiently with, for example, super Eddington accretion or are limited by the Eddington accretion, and therefore you need a higher black hole seed mass. These are still, a lot of arguments there. Now, when we look at, the redshift 14 galaxy that was the redshift holder, it's still officially, I guess, but, here what we are looking at is basically this very strong break and maybe a weak, C3 line there. I think the nice thing is that one can now use other telescopes such as ALMA to follow up these galaxies. And so what is shown here is the oxygen 388 micron line here, and you can see that even from this spectrum before, we had a probability distribution for the redshift that peaked at slightly lower redshift, at slightly higher redshift, and the spectroscopic confirmation shows that it's, with the emission line is slightly off. And the reason for this is that we have basically a damping wing from the neutral gas that starts eating away more and more of the, alpha line, but also some of the very bluest part of the spectrum, which makes the exact measurement from the redshift from this break quite difficult. Again, this galaxy is large, we think, it's 200 parsec. So there is also basically no strong indication for an AGN. But we can use now the, oxygen 3 line to basically measure chemical abundances. And again, it's quite interesting to see basically that this galaxy, lines up basically with other similar galaxies at a similar redshift there. An interesting question, of course, is how old are the stars? How massive is this galaxy? And for this, we can combine JWST, NIRSpec and NIRCam together with MIRI observations. Again, this galaxy is very bright here. And we can use this MIRI flux because it is basically boosted by oxygen 3 and H beta together with the ALMA data to constrain a rough estimate of the star formation history of this galaxy. And what you can see is that we think that this galaxy have a quite extended star formation history of maybe a few tens up to maybe 100 million years. And so again, this would indicate that we might have already initial star formation in such systems as early as redshift 20. So this is basically showing you a few example galaxies of this very high redshift universe. I want to move now a slightly lower redshift. And the idea is that when we move to the epoch of ionization, we have access to the rest frame optical, and we can hopefully learn a bit more about the stellar populations, and in particular also the variability of star formation and the regulation of star formation. So the very fundamental idea goes back basically from thinking about galaxy evolution in the local universe up to maybe cosmic noon, where we think the star formation is kind of self-regulated, where we have inflow and outflows, and there's basically a self-regulation equilibrium of how galaxies evolve along the relation between star formation rate and stellar mass, the so-called star forming main sequence, where we think galaxies basically move up and down until they are massive and then quench and form massive red and quiescent galaxies. Now the question, of course, is this picture still holding when we go to earlier cosmic times? And so when you think about variability, or changes of star formation rate on certain timescales, a useful way to quantify this is looking at the power spectrum of the star formation rate fluctuations, right? So we can imagine that if you have very bursty star formation, you have a lot of power on short timescales. If you have, very continuous star formation, you might have a lot of power on longer timescales. And so we built this extended regulator model. The idea is very simple. You have on longer timescales, you are driven basically by an external mode, mostly by inflow. Okay, so you're driving star formation because you are adding more and more gas to the system. But then the internal process is also important. You have an internal part where you basically form stars in GMC, and you're sampling, a kind of a stellar cluster or a GMC mass function. And so this gives you basically a way to think about bursty star formation, in particular at high redshifts, where maybe we are not able to spatially resolve star formation as well as we do in the local universe, where we can really see GMCs forming, being there, and also being disrupted. In high redshift, maybe everything is unresolved, and we have to, instead of going to the spatial scales, to the temporal scale. And so when you think about bursty star formation, you can, think of it as basically maybe the star formation burstiness is driven by stochastic inflow, right? You are randomly feeding the galaxy, and that's how the galaxy reacts and has bursts in star formation. Or it might be related to sampling individual star forming regions, more like when you think about dwarf galaxies, where you see individual star clusters, turning on and off, right? You might have bursty star formation because of that. And so this shows you basically the realization of such a very simple toy model, where we are kind of in the small, low mass galaxy regime, maybe at high redshift or low redshift. This shows the distance from the main sequence, and you have these really strong bursts, basically, where galaxies turn on and turn off and turn off, and so on. Milky Way galaxies might be, much more continuous. We have cosmic noon galaxies. It might also be a bit variable, but again, on much longer time scales, and kind of more high C massive galaxies, maybe similar to cosmic noon, but on shorter time scales. And so the way that we want to then estimate this, I mean, let's put it this way. In theory, of course, we can follow galaxies through time. That's great. When we are observers, we see the galaxies on the sky and they don't really change, right? At least not in our human lifetime. And so what do we need to do? We need to basically use something like ergodicity, where we try to turn things around and say, well, let me now go and measure the star formation rate on different time scales, right? You can imagine that if you have a short time indicator, like H alpha, you're able to basically see a large diversity, right, in these bursts. But if you average a star formation over 100 million years or 200 million years, you're averaging out different cycles, and all of it will collapse. And this is basically shown here, that these different star formation histories look very different if you try to estimate the scatter in this relation in the main sequence, basically. You can see that the longer you're averaging the star formation rate over, the less and less scatter you will have. And this depends on the burstiness, on the variability itself. Now, a small detail that might be important, especially when you think about high redshifts, is that whenever you measure the scatter, okay, so this is basically both scatter because of short fluctuations, for example, on a given time scale, but it can also be a contribution from longer modes, right? Because you have a star formation history of a galaxy, it might have long modes, and on top you have short modes. If you think about burstiness, you want to kind of subtract, right? You want to subtract these long modes and just measure the short modes. And so if you want to measure burstiness, it's really kind of this difference here. You want to make sure that whatever you measure as a scatter here, you need to subtract this on longer time scale. So let's do this first in theoretical models. This is showing some results from the THESAN-zoom simulations from Will, who is a PhD student. And again, this shows you basically this averaging time scale versus the scatter of the main sequence from low masses to higher and higher masses. So you can see that the scatter slightly decreases as you go to higher masses, but there is also a redshift effect. And the redshift effect is kind of opposite, which you might have expected, right? When you look at redshift, you can see that when you go for these low mass galaxies, at highest redshift, the scatter was actually smaller, and then the scatter gets larger if you go to lower redshift. So why is that? And the idea now is that we can, this is showing the same thing basically. You can go and see that the scatter on 10 million years basically increases with time. And we can now decouple this between understanding what drives the inflow, right? So what's coming in basically from the outside of the galaxy into the galaxy when it comes to gas. And we can compare this also with the internal variability, so driven by star formation process. And you can see that this increase in the scatter is mostly driven by inflows. You have larger and larger diversity of galaxy populations at lower redshift. Some of them are having more inflow, others have lower inflow, and this drives basically the scatter, whereas the internal one stays more or less constant. So this is again not burstiness, right? This is really just diversity and scatter. We can, of course, now try to subtract the longer time scales, and this is what is basically shown here. This is, burstiness, so we're looking at the difference between the scatter on 10 million years to 50 million years. And what you can see here, there is really that, the scatter basically, this burstiness, decreases with cosmic time. So we had basically burstier star formation at high redshift. It flattens and is rather flat. And again, the inflow doesn't really contribute much to this at low redshifts. It's maybe important at higher redshift, but it's mostly driven by the internal process. So now a detail, but a very important detail, it's actually thinking about the extreme outliers of a population, right? So the scatter shows you basically what the overall population is doing, and you try to quantify the distribution of that. But you can also look at outliers. And I think a very interesting population is actually the galaxies that are well below the star forming main sequence. So these are galaxies that have very low star formation rate given their mass. And so we again expect basically most of the different models, that are a few percent of those galaxies that are somewhere between 10 to the 7 and 10 to the 9 and form basically very little stars. They are in this phase only for a very short amount of time, so typically a few tens of millions of years, so maybe 10, 20 million years. And so we call this, we termed this idea or this temporally quiescent phase mini quenched, right? So these are not quiescent galaxies as we discussed in the massive end where we have quenching for a long time. They are just basically part of this burst cycle and then on this low phase, and they can stay down there for quite some time. Okay, I can talk much more about how we try to observe this. I skipped this, but I'm very happy to talk about kind of the problems on the observational side of this. So let's ignore this for the moment and let's assume we can do a lot of the things we're trying to do. So first of all, it's quite easy actually with JWST to find bursty systems, right? Here are the bright ones. We can see them with spectroscopy and we can measure their star formation histories. And this is shown here in a few examples. We can look at equivalent line distributions. And what you typically find is that the lower the mass you have in a galaxy, the higher is the star formation rate of 10 million years divided by the star formation over 100 million years, right? And so again, you have to be careful with not overinterpreting this. This indeed shows that we have many galaxies increasing their star formation at low masses, but we probably miss observationally all these galaxies, right? All the galaxies are downturning their star formation rates. They will be very faint and they will be really hard to observe. And you can show that basically we are basic complete above 10 to the 9, we are partially complete to 10 to the 8, and then really incomplete below 10 to the 8. Okay, so these kind of trends have to be interpreted with a lot of care. Now, I told you before about these phases where we have a burst of star formation, then a quenched phase, a low star formation phase, and this is shown an example here from Tobias Loser, who graduated last year. And again, this shows you basically the star formation history we infer by fitting the spectrum and the photometry. You can see that you had this increase in the star formation rate and then this very drastic drop, giving rise to these absorption lines and also the 4,000 angstrom break you can see here. And again, this galaxy is quiescent, basically. It basically has no star formation. You can go to trying to measure, a star formation from H beta, and you get an upper limit of 0.1 solar masses per year. And again, these galaxies are only 10 to the 8, 10 to the 9 solar masses, right? So we clearly see that there are these, galaxies that are low mass and quiescent. Now, we don't know whether this galaxy is really just temporarily quenched. However, we find galaxies that are basically just starting to shine again. You can see an example here by Callum Witten, again, graduated last year. Again, you can see basically here in this spectrum that we have, a Balmer break, but we also have now, some emission lines turning on. When you look at the emission lines and try to infer what ionizes these emission lines, we basically can rule out, that this is driven by HEN. It's really star formation. And so when you fit this now with, things like prospector, you can again see there was this upturn, there was a downturn in order to explain basically the UV. And then you have a very recent upshoot in the star formation last 5 to 10 million years. So again, this is basically maybe the, how this other galaxy might evolve into. So you see that these are basic galaxies that are turning on very recently. Now, in order to go to do this kind of work on statistical samples, we rely still on photometry. We try to include spectroscopic samples as much as we can, but typically, we have only about 1 to 2% of the sample having spectroscopy. However, in many of our fields now with JADES, for example, we have really exquisite photometry, right? So here we're talking about broadband photometry, but also medium band photometry, which really helps to actually estimate emission line strengths very accurately. And so this is shown here, 2 examples. So here, for example, we see no emission lines present. In this galaxy, we see emission lines present, and you can start trying to do basically constrain their star formation histories, taking into account, basically variations in the dust attenuation law, in emission lines, being arising from different gas phase metallicities, and so on and so on. And again, this is basically showing you the specific star formation rate as a function of mass. And again, I told you already that, we see this upturn towards lower and lower masses. And again, we really have to focus on this regime if you want to be complete. Here, we can still study the galaxy population because we really trace still also quite lowly star-forming galaxies. But down here, this cutoff here that you see is probably induced by our observational limitation. And so what I'll show you here, and again, this is very preliminary work that we try to wrap up in the next few weeks. This shows you the specific star formation as a function of redshift with some of the literature work at lower redshift and then our measurements at high redshifts. And what we find is that, the overall shape, when we fit it with a simple power law, depending on mass and redshift, we find that the specific star formation rate keeps rising basically, and it follows roughly a power law, of 1 plus c to the power of 2 to 2.5, which is very close to what you would expect from specific mass accretion rates of dark matter halos as well. And this is basically shown here with this dotted line here. So basically, it's basically the same shift. It's just slightly offset here. But the overall evolution of the specific star formation rate at fixed stellar mass is very consistent with the idea that you have just higher and higher accretion rates onto these systems. Now, again, if you look at the numbers, you're entering here very high specific star formation rate, of about 10 per giga year, again, implying that you have mass doubling timescales of the order of about 100 million years. So these galaxies are really growing very, very rapidly. And so now we can go and try to estimate the scatter. And again, we do the same game as I kind of explained before. We can go and estimate the scatter as a function of redshift for different averaging timescales. Again, here you can think of it like we're trying to just use the H alpha emission line strengths, whereas here we are relying much more on the UV. And you can see that basically the scatter, the intrinsic scatter decreases if you go to longer averaging timescale. But there's overall quite weak evolution in redshift and also in stellar mass. Now, this is, I think, the interesting part is showing the short-term variability or the burstiness, right? Showing you basically a difference between 10 to 50 million years in the scatter. And you can see that the burstiness might have decreased, from redshift 8 to redshift 7. Again, we are still very much working on this. And then it has been rather flat, maybe slightly increasing. And so we try to understand this now, what drives this. And I told you already the observations, that the models might be able to reproduce these kind of trends, that the burstiness might be first driven by, more inflow-related processes that are maybe acting at high redshifts on short time scales, and later on, maybe you're more star formation driven. So this was about star formation regulation, and of course, tightly linked, that I already mentioned before, is kind of the morphological evolution. And so in the next 5 to 10 minutes, I want to kind of highlight what do we learn about the structure of these early galaxies. And the first thing that you might be interested in understanding is like actually how are these galaxies growing? I told you they grow bottom up, but then I already told you that we look at star formation. So you might be interested to understand how many galaxies are actually merging. And so for this, in order to estimate the merger rate, so how often galaxies actually merge together, we use a pair method, worked by David Puskas. And what you see here is like kind of a tumor sequence, right? Going from large separation to smaller and smaller separation, basically. And so we had to do a very careful completeness analysis to understand, how many of these pairs do we see and how many could we see and so on. And this shows you basically the key result. Again, here we have to take the pair fraction and convolve it with a merger timescale. And when we do this, we get the merger rate as a function of redshift. These are basically our measurements from high redshift. The color coding shows you different stellar masses. And this also compares to lower redshift measurements from redshift 0 to redshift 3. What you might see is that the merger rate actually increases and increases, and so you can see that typical values here are somewhere between 1 and 10 per giga year. So this means that if you take a typical galaxy in the early universe, it has about 1 to 10 major mergers. Okay, so this is the typical number to keep in mind. So if you look at the galaxy at redshift 6, you would expect a few major mergers to have taken place. With major merger, I mean masses of 1 to 4 or larger. Now, what is interesting to do is actually compare this with the specific mass accretion rate, right? How much mass do these mergers actually bring in, right? They're happening. So what is the typical mass ratio? 1 to 4. We put this together and we can estimate what the specific mass accretion rate is, which of course can be then compared with the specific accretion rate, right? With the star formation taking place in the galaxy. And so I showed you before that we can compare this with basically, the specific star formation measurements and, observations from different surveys. And what you can see is that the specific star formation rate in the early universe is rising and rising up to about, 10 per giga year, which is always larger than what we see in the merger rate. And so this implies already from this simple analysis that we think that the in situ star formation is more important than the mass that you bring in through mergers. And so we can actually, integrate this and, build a simple model. And when we do this, we can estimate what the typical exit to mass fraction is of these systems. And again, we measure exit to mass fractions, or estimate exit to mass fractions of the order about, 10% or so. And then, of course, when you have a quenching threshold, then it starts to shoot up, and you really are dominated by major mergers at the massive end. Now, this doesn't mean that mergers are not important for driving star formation, right? It could still be that mergers, don't bring in a lot of stellar mass, but it could still be that they bring in a lot of gas, and this, of course, then drives the star formation. And this is something that we are trying to understand and look into by studying whether the star formation rate is enhanced in mergers versus non-mergers. Another thing when we think about, the early evolution, because I told you about the pair fraction, which looks at galaxies in some separation, is of course trying to understand what happens when the mergers really come close together and building up the kinematics, right, of the galaxies. And so we have been looking into this from the NIRCam side. So this is GRISM observations, where you basically take an image and you disperse it in one direction. And Lola has been writing Gecko, which is a GRISM emission line kinematics tool. It's a tool that basically allows you to forward model these kind of data sets, right? So you have basically in the observations of the GRISM, you have convolved the morphology, the emission line map, together with the kinematics, and you need to deconvolve these two components. And so we do this in a forward modeling approach, where we then fit basically observed GRISM with a model, and we can tease out the emission line distribution and the kinematics separately. And this is showing you some of these nice posterior distribution diagrams. And so we can measure things like, for the ionized gas, the velocity dispersion, as well as the rotational support for these galaxies. And so this is showing you some of the summary. So it's a bit small, but basically what this shows you is, again, we have now roughly 300 galaxies between redshifts 4 to 6. Okay, and this shows you basically individual measurements, including upper or lower limits, and the median trends of that. And you can see that basically the velocity dispersions we are inferring, are somewhere between 50 to 200 kilometers per second. So there's a large diversity. And when we look at V over sigma, the rotational support, we measure proper, typical values somewhere between 0.2 to 5. So we see some of the galaxies are indeed well in the kind of rotationally supported regime. So they are disks, but the majority lies kind of in this intermediate region, or even below this, which are clearly dispersion dominated. So thinking about this in the more, cosmological context, how does this ionized gas kinematics consistent with other surveys? So this shows you basically not individual measurements. These are really surveys that have, taken decades to build from, Symphony and CMOS. You see basically the velocity, divided by sigma. So basically the rotational support as a function of redshift has been basically decreasing from higher redshift to lower redshift, which has been very nicely reproduced by the illustrious TNG model, by people in this room here, where you basically see that V over sigma of the ionized gas really decreases. And we basically find measurements that are kind of consistent with this, right? So with, a decreasing trend going to higher and higher redshift. Now, when we look at, other gas measurements, and again, there has been a lot of, stuff in the literature. Now you can see maybe there's a difference between the colors of the symbols, right? So there are kind of blue and then the orange symbols. The blue ones show you basically the ones that are from ALMA, from cold gas tracers. And those typically, you can see that they are probing slightly higher V over sigma. So in ALMA, we have observed many more rotationally supported systems. Now, you can argue, maybe this is because of a tracer, right? Maybe with the ionized gas, we are tracing also outflows and other things, whereas in the cold phase, we are not seeing that. However, another important difference is the stellar mass. So typically, these systems here are rather massive, in particular at high redshift. So we have to be quite careful of when we compare galaxies across cosmic time, that we are looking at similar mass galaxies, and not overinterpret any trend that we see with redshift that could be introduced by a stellar mass evolution. We can, compute from this the disk fraction. So basically, if you count the galaxies that are, rotationally supported versus not rotationally supported, of course, it depends on your threshold, right? So if you take V over sigma of larger than 1, you have basically a disk fraction of nearly 40%. If you are have a more stringent criteria of, V over sigma of 3, right, then you drop this significantly to only about, 20%. I think the nice thing is that when we look at the velocity dispersion, the dominated systems, they are really in the majority of roughly 50%. And then we also had clear indications for mergers, right, where we can see basically 2 clumps and large velocity gradients in those systems basically make about 10%. And it's nice to compare this to, the pair fraction method that I mentioned to you before, and this is roughly in the same ballpark here. Okay, so last but not least, my favorite topic is understanding spatially resolved star formation at high redshifts. And this is very challenging because, as you have seen in many of the images, galaxies are really, really compact. And so any kind of gradient is really difficult to measure. So I want to show you some of the early work that William has been doing, was a PhD student, moved now to DARC, to Copenhagen as a DARC fellow there. And we basically look into this galaxy here because when we looked at the image in different filters, we could clearly see that there is some kind of color gradient in this system. And so what we have been doing is we have been we measured the color gradient by forward modeling the light distribution in different components. We had a core, okay, so this is nearly basically a point source in the center. We have kind of an extended component, and which we can call disk, because the surface index of that component was roughly 1. And then we also have the clump that we also fit. So we had these 3 different components, forward model all the filters, both medium band and broadband photometry. And then we fitted the SEDs of these components and measured the star formation histories. And you can see that the disk here, you can see it has kind of a rising star formation history, whereas the core here was high, but it seems to be slightly decreasing. And the main reason why we can measure this is through basically the emission line strength. So what we can do now is we can go and measure profiles of this because we have the morphological distribution of the light, and then we measure the SEDs, and we can measure stellar mass surface densities of these galaxies. And what you see here is in black the combined core plus disk profile of this galaxy, and I show you here this is stellar mass surface density as a function of radius. And again, this galaxy is very compact, right? It has a size of only, basically 200 parsec or so, and so it's very compact. But the stellar density in the core is really, really high. Okay, so if you compare, the stellar mass that we measure with the size, we infer very high densities that are actually comparable to local elliptical. However, when you compare this to local ellipticals, such as these, gray dotted and dashed points here, you can see that you're missing, of course, a lot of stellar mass because the galaxy has only, a stellar mass of about 10 to the 8 solar masses. And so it's just putting into perspective that the cores of these kind of systems might form very, very early, but they still need to grow inside out first due to star formation, which we see maybe in the disk, that is more extended, and then maybe through minor mergers later on once they are quiescent. And just to see this a bit more on spatial resolved scale, so this shows you the specific star formation that is a function of radius for this galaxy, and this shows you the combined profile. You can see that in the central part, this galaxy is still growing, but the specific star formation is kind of low, implying doubling timescales about 200 million years. But then in the outskirts, we have specific star formation that imply doubling timescales of about 10 million years. So it might be that this is, really growing very rapidly in the outskirts and not that much in the core. And so now at the moment, we're trying to push this to much larger data sets. And this is ongoing work where we try to measure sizes and profiles for these different profiles. So UV, far UV, near UV, and optical, and also for DH alpha. And this is a lot of work that we are currently pushing. Okay, so I need to wrap up. So exciting ahead, moons, I think, right? So we can do detailed characteristic of the cosmic web and cell populations there. Again, just to give you a bit of an idea that, we're really entering basically now, a lot of data mining projects, basically really getting orders of magnitude more spectra, even beyond, redshifts 1, basically, not just in the local universe. And then, of course, the big thing is ELT that is really being actively built. And at the Cavendish Laboratories or in Cambridge, we are very much working on NDIS and the deployment of that. Okay, so this is the summary, and I think I'm running out of time, so I'm just letting them there, but I'm of course very happy to answer any kind of questions you might have. Thank you.
Great, thank you very much. I'm happy to take questions, particularly students and postdocs to start.
In the beginning and also in the end about these galaxies, and you said like 200 parsec was extended. So were the galaxies so tiny at those times? Or?
Yes. So so you have to be very careful when I talk about these galaxies, when she talks about these galaxies. I think that again we get a better handle on the kinematics of many of these systems. Okay, and we see rotational support sometimes, but indeed typically galaxies are much more compact. Okay, at these early cosmic times. they're smaller both in stellar mass typically, but also in size. And so I think that, what happens is the galaxies really grow, potentially to some degree also inside out, where we see then galaxies getting larger with time, in size, but also in mass. Now, these are not really, again, how much these galaxies and how they compare with the local universe, I think is quite difficult. You have to imagine that many of the galaxies we're observing at these early times, they will grow to be 10 to the 11 by redshift 2. And so then they will quench and will be early type galaxies, quiescent galaxies, maybe faster rotating galaxies. And then when they have a major merge, they might end up to be, at the very massive end. So these galaxies, these galaxies that we might see at redshift, 6 or so, they don't end up as being local disk galaxies. Some of them might, but not most of them.
More questions?
Hey, thanks for the cool talk. So what is the completeness for your pair fraction counting? How do you select your galaxies to ensure you have some level of completeness at some point?
Yeah, so we go down to 10 to the 8 solar mass. Okay, so that's basically the mass limit where we think that we can, find and count those pairs accurately. We still try to, assess this in more detail when we think about bursty star formation and so on, because it's really challenging to actually understand what is the true population and, what model should we use to describe the true population from which we then do a completeness analysis and completeness study. But what we have done in that work by, the rather brave assumption that we take the mass to light ratios that we, for the observed galaxies, extrapolate it down and then estimate basically what the completeness limit is. So similar to what has been done previously, based on work by Bozzetti in 2010 and so on. And that's basically the mass limit where we think we can measure properties.
Thank you for the talk. The question that comes to me is, what about stellar populations? You try to estimate from the photometry the star formation rate and the other parameters. And my question is, what about the stellar population synthesis models?
Yeah.
At the beginning of the talk, you stressed that the population 3 stars may set in. And now my question is, wouldn't it be necessary to include the population 3 stars in the stellar population synthesis models in order to derive the formation efficiency and the star formation rate? Now you are talking about redshift record holders at redshift 10 and even redshift 15. And my question is, what is the maximum redshift you would buy it that you would still use normal star formation stellar population synthesis models without paying attention or without putting advantage to include these population 3 stars?
Yes. So I think that's an excellent question. We have been experimenting with population 3 star models. However, even for this redshift 14 galaxy where we detect oxygen 3 at 80 micron and, even see the boosting in the MIRI data where we infer, a gas-phase metallicity, the gas-phase metallicity there is 10% solar already. And so overall, it seems that these galaxies, everywhere we can, rather reliably infer metallicity, seems to be rather high. It doesn't mean that, we don't have, extreme star populations, both when it comes to POP3 maybe, and the contribution of those, or a change in the IMF, and we have more massive stars that maybe, are more dominant. Or we even have, I think more importantly, what we know that we have for sure to include is, alpha enhancement in the models as well. So when it comes to the detailed chemical elements. And so, yes, these are all caveats and things that one is working on. So the POP3 models can be quite quickly fit to those properties. But again, you cannot get an oxygen 3 80 micron line with pure POP3 models. And similarly, people have been trying to go to much more exotic models like dark stars, and they have fitted these galaxies and so on. But again, when you look at the details there, with the emission lines you observe, you cannot reproduce those. But I agree that one has to explore, non-standard models. it seems that the universe enriches very, very quickly. At least from the things that we have seen, it's very, very difficult to find systems that are, POP3 dominated. We have been looking quite hard because this is what we want to find, but it's very challenging to find that.
Any questions from?
Thank you. That's an amazing tour de force. Congratulations. Question, you do the prospector modeling of what I will call intermediate redshift galaxies, maybe 2 or something like that.
Yeah.
So you will have in your look back time bins corresponding to the in situ observations you're making with JADES at the high redshift. Can you compare those numbers and extract information on bursty versus continuous and stuff like that for the Z14 population?
Do you mean going from slightly lower redshift to higher redshift? And
Yeah, so you might be able to see what's happening after 500 million years in one of your bins in your prospector, and how does it compare with your source counts that you actually see?
Yeah. So such tests have been done at redshifts of basically 1 to 3, quite in detail, understanding, can we take the galaxy mass function, the star formation histories, and basically predict how it would look at higher redshifts and do delta comparison. And that's why I think the prospector gained a lot of traction also, because some of these tests are very successful in comparison with previous claims when it comes to solar ages and so on. At higher redshift, that's something that actually I'm actively working on. Again, their completeness is very important to understand, because again, we have a handful of objects, and so the question is how representative are they and so on. But this is something that I think is very interesting to understand. We can look at their redshift 8 and extrapolate the cosmic star formation density back in time and see whether this is consistent with what we see directly. And I think this is exactly some things that we want to do. Yeah, so there is some studies that we have been doing, for example, for quiescent galaxies. So, again, I didn't have time to talk about massive galaxies and massive quiescent galaxies, the first quiescent galaxy that observed at redshift 3 to 4. And when we take the star formation histories of those, if you take certain set population models, you predict galaxies to have thousands of solar masses per year of star formation at redshift 10, and this is something that we don't observe. And so there is an interesting question about whether we should choose priors that disfavor such galaxies. And so this is again something that we try to currently understand what kind of prior should we use so that we basically have galaxies and models for galaxies that are self-consistent, as you say. Yeah.
Questions? Are there any questions online? No.
Hi, thanks for the talk. I mean, it's spectacular to see all the galaxies in high redshift, but for someone who works with the local universe where we don't even use redshift, how do we link those galaxies with, for example, present day elliptical galaxies or cluster center galaxies? For example, you say here the merger does not contribute significantly to the mass growth. Does it actually provide profound impact on how we understand the formation channel of elliptical galaxies nowadays?
So, okay. So this is particularly focusing on at high redshifts, but so again, so the things that you're looking at high redshift, typically the typical galaxy masses are somewhere between 10 to the 8, 10 to the 9, and then sometimes 10 to the 10. And there are a few exceptional cases where we start probing 10 to the 11 solar mass galaxies as well. Now, when we think about the mergers of these systems, again, we're looking here at systems between 10 to the 8 and 10 to the 10 solar masses. If we build a model where we integrate this up, you would get an exit to mass fraction that stays rather low. However, then if you say, well, at some point you quench the star formation in galaxies, right? You're just switching it off, and you keep integrating the merger rate, right? You would very naturally, very automatically, get an exit to mass fraction that just starts increasing, because above this mass you can just grow only by merger. And so in such a some very simple scenario where you just quench the star formation around 10 to the 10.5 or 10 to the 10 11, then you have a very very natural way of producing slow rotators and massive ellipticals in the local universe, basically. Okay. Now this is not really the parameter space we can probe, but you can self-consistently reproduce it if you would just quench galaxies at this threshold.
We have a question over on this side of the
Yes.
room.
Beautiful stuff, Sandro. if you had to, so it looks in many ways like a beautiful firming up of the picture. What do you think are, from your perspective, the biggest surprises or the things where things need more than just tweaking of our understanding, but really new physical mechanisms or anything along those lines?
Yeah, that's a good question, of course. Yeah, so, well, sorry, where was this? This was, yeah, blah, blah, blah. I've worked mostly at lower redshift, right? Redshift 1, 2, 3, and then, I thought like I'm going maybe to redshift 6, 7, 8, where we can still do a bit of physics. But I was really kind of intrigued by those systems, right? So I think there is still a lot to learn about really how do the first galaxies, come to be being so bright already. And I think there is still a lot of open questions about, this early black hole growth and how quickly, these black holes grow. And I didn't even touch on the topic of, little red dots and LRDs, right? So I think there is a very interesting, there's still the question of like, how do you link dark matter halos, to the star formation and the star formation recipes, but then also to the black hole seeding and black hole growth. And then, how we see that, right, observationally. I think there are a lot of open questions there because again, as we just touched on, like, we assume some simple models to infer galaxy properties and we try to count degeneracies. But I think that, these systems are really diverse, and understanding this diversity, I think, you need maybe, better models, maybe new physical recipes. Yeah, I think that's very, very intriguing for me at the moment.
Hey, thanks for your talk, first of all. This question might be going in a bit different direction, but I was wondering, you mentioned in the beginning that you're assuming lambda CDM. And there's some tension which is talked about, and I guess one can't be sure if it's really there or not. There are new surveys which, like kits, which resolve that tension already. But in this analysis you're doing, what would you say are the minimal assumptions you have to take about the cosmological model to get a useful analysis?
Well, we need a cosmology to work in. Thinking here, the big movement or things that people try to play around with, of course, is the number density of dark matter halos, and there, you can, one thing that we explored in the past is looking, as constraints, like how constraining are early galaxy counts for warm versus cold dark matter, right? And what we conclude is that you can change star formation efficiency, or you change cosmology, and you have perfect, degeneracy, basically. I think if you have, again, that's why I would never use galaxies to claim a change, a need for changing cosmology. Although we have been looking at, for example, early dark energy, which, again, can boost very naturally the number densities of dark matter halos in the early times, and then converge back onto normal dark matter halos, at lower redshifts, and you can, ease the constraints you get, have on the star formation efficiency, for example. But yeah, it's challenging and difficult. I think that at the end, lambda CDM needs to be extended, right? Especially if lambda is not constant, and neutrino have masses and so on. Like, there will be changes to this anyway, and we might have to adopt, because we rely for every physical property we measure on the cosmology at the end of the day.
Okay, I don't see any more hands. So let me quickly announce that there will be, with the students and postdocs, drinks after, that's organized by Marco. So feel free to come down here if you're interested in joining that. And there'll be dinner at DeMario at 7:30. You're also welcome to join if you're interested in that. So that's it. Let's thank Sandro again.
Yeah, thank you. Yeah.